so this is my solution to 6.4.1. We are told that there's an inverted right cone that is filled with hot chocolate, and the cone has a radius of 4 meters, a height of 5 meters, and it's filled with hot chocolate to 3 meters. So we're asked what the work done is to empty the tank. And we're told that the density of hot chocolate is 1,070 kilograms per meter cubed. So work is force times distance, and force is mass times acceleration, and mass is density times volume. So to calculate the work done, we're going to do density times volume times acceleration times distance. So if we wanted to calculate the work done to empty out just one representative slice, we would do 1,070 kilograms per meter cubed times the volume, which is just pi r squared, times the tiny change in height, which is just delta h. And then our acceleration is just acceleration due to gravity, which on Earth is 9.8 meters per second squared. And our distance is just going to be 5, which is the total height, minus whatever our height is. So it's just 5 minus h. So this looks good, except there's one problem. We need everything in terms of h, and this r squared right here, we wouldn't be able to integrate if we kept it. So we need to put it in terms of h. So to do that, we're going to notice that we have some similar triangles in this cone. So this big triangle is made from the total radius and the total height, which is just 4 and 5. And then we have the smaller triangle here, which is made by whatever radius we're choosing and whatever height we're choosing, and that's just r and h. So we get the ratio that 4 over 5 is equal to r over h. So our radius, we can put in terms of h, is just 4/5 h. So now we know that our volume is 4/5 h squared pi times our tiny change in h, delta h. So now we are ready to integrate to find the total work done to empty out this massive tank of hot chocolate. So we know that there's got to be an integral. And so our bounds. We're not emptying the whole tank because we only filled it to 3 meters. So we're just emptying it from 0 to 3. Those are our bounds. And then we're going to do our density. And then we will have the volume, which is 4/5 h squared. And then we are going to have our acceleration due to gravity, which is our 9.8. And of course our distance, which is 5 minus h. And then we are going to have this in terms of h. So we have our dh. And so then when we actually go to evaluate that, we get that it's approximately a really big number. So it looks like it is 521,813-ish joules. And just sort of as a side to this, if we wanted to check that we kind of got the right idea, or got this correctly, we could check to make sure that our units line up. So we know that density is measured in kilograms per meter cubed. We know that our volume is measured in meters cubed. And we know that acceleration is measured in meters per second squared. know that our distance is just simply going to be measured in meters. So this cancels, and we're just left with kilograms times meters squared over seconds squared, which is indeed joules. So we at least know that we kind of got the right track of our joules being correct. So that is the work done to empty out this ginormous tank of hot chocolate, which I really wish I had of right about now. All right, so that's it.